Section 5.1 is on antiderivatives and indefinite integrals. What we're going to learn is to understand the definition of an antiderivative and use indefinite integral notation for antiderivatives. We're going to use basic integration rules to find antiderivatives. We're going to use initial conditions to find particular solutions of indefinite integrals, which leads its way to the next one, which is use antiderivatives to solve real-life problems. So let's take a step back and think about what we've been doing the entire semester. For the entire semester so far, we've been starting off with a function, and once you find the function, we've learned all the rules to find a derivative of a function. So for instance, let me give you an example. Consider the function x squared. When we take the derivative of x squared using the power rule, we would get 2x. So the entire semester, we've been going from the function to the derivative. For this chapter, we're going to be, in the last chapter of this class, we're going to be going the other direction. If I give you the derivative of a function, can you give me the original function? So if I told you the derivative was 2x, what was the original function? The answer would be x squared. We could do other examples as well that we've learned. For instance, what's the derivative of e to the x? Well, the answer is e to the x. So if the derivative of e to the x is e to the x, then the antiderivative, which is the other direction, the antiderivative of e to the x is also e to the x. So now what we need to do is go through all our derivative rules and essentially do everything that we've been doing backwards. Okay, so let's take a look. It says, so far we've been asking, given a function, find its derivative. Some important applications of calculus involve the inverse problem. Given a derivative, find the function. That is, given f of x, find capital F of x. So given lowercase f of x, find capital F of x such that the derivative of capital F of x is lowercase f of x. We call this process anti-differentiation. Okay, so we've been using the notation f of x and f prime of x. Where we see f prime of x, they're going to use lowercase f, and where we see f of x, the original function, they're going to use capital F. So just to let you know, capital F is always the original, lowercase f is always the derivative. So it says a function, capital F, is the antiderivative of a function, lowercase f. When every x in the domain of lowercase f, it follows that the derivative of capital F is lowercase f. In other words, an antiderivative is if you take the derivative of the original function, you get the derivative function that you started with, okay? So let's look at the example right here. Well, this is the example one of the examples that we just talked about. It says find an antiderivative of the following functions. So it says f of x equals 2 to the x. In other words, what function can I take the derivative of? That's what antiderivative means. What function could I take the derivative of and get 2x? Well, we noticed that the answer was already x squared. But I want to challenge yourself to think of, is there anything else? Take a moment. Pause this video and think, is there any other function that would work? So I found another function that would work. How about something like x squared plus 5? Notice if I take the derivative of x squared plus 5, the derivative of x squared is 2x and the derivative of 5 is 0. So I would get 2x, which satisfies the conditions. So x squared plus 5 is an antiderivative of f of x. Let's look at g of x. How about 4x cubed? Can you find a function that when you take its derivative, you get 4x cubed? Well, most of you are probably thinking of, hey, x to the fourth would work, because if I take the derivative of x to the fourth, I would get 4x cubed, but I'm going to try something different. How about x to the fourth minus 7? Again, the derivative of x to the fourth minus 7 is 4x cubed, so x to the fourth minus 7 is an antiderivative of 4x cubed. C is another example that we already talked about. How about e to the x? What can you take the derivative of and get e to the x? Well, I know an answer is e to the x, but how about something like e to the x plus 13? Does that work as well? E to the x, the derivative of e to the x is e to the x. The derivative of 13, because it's a constant, is 0. So e to the x plus 13 is antiderivative of e to the x. Okay, so let's look at this next question. It says, compare your answers with your neighbor. Are your answers the same? Can there be more than one answer? Explain. So for instance, look at part A. I said x squared plus 5. Most of you probably just said x squared. But think about x squared plus or minus any constant number. The derivative of x squared plus or minus any constant would be 2x, because the derivative of x squared is 2x and the derivative of a constant is 0. So how many answers could there be? How many antiderivatives could there be? Well, this constant right here, where I put plus 5, could be any number that we want. Any constant number that we want. So what we generally do is, instead of writing x squared or x squared plus 5, we write x squared plus c as the antiderivative for 2x. The reason why is because for any constant c, the derivative of x squared plus c is 2x. So this right here is the family of functions. X squared plus c is the family of functions that are antiderivatives. There's never one answer. There's actually an infinite number of answers to every single antiderivative problem. So it says the antidifferentiation process is also called integration. That's what I'm going to be calling it most likely from here on out, is integration. It says the antidifferentiation process can also be called integration, as is denoted by, well, here's the symbol right here. It looks kind of like an elongated S. That's called your integral sign. So just like we've seen d dx for derivative, or that f prime of x, when you see this symbol right here, this long-looking S symbol, that is an integral sign, and it means find the antiderivative. So when you look at this part right here, where you see the integral sign f of x dx, that's called the indefinite integral. Indefinite integral, anytime you see this, what I want you guys to remember is that you're going to be putting a plus c in your final answer. So this is find a function where its derivative is f of x. So for instance, above, what we determined is the indefinite integral of 2x with respect to x. That's how you say it in mathematics, the indefinite integral of 2x with respect to x. What this means, though, is what function do you take the derivative of and get to x? We determined that the answer is x squared, but even further, it's x squared plus any arbitrary constant. So the antiderivative, or indefinite integral, of 2x dx is x squared plus c. The beautiful thing about this is the entire semester we have not been able to check our answers unless we use other technology. Now we can finally check our answers. How do we check our answers? Well, the idea is we want to differentiate our answer. So if I take the derivative with respect to x of x squared plus any constant, I would get 2x, and then the derivative of constant is 0. And the key here, what I'm looking for, is when I take the derivative, do I get the original function that was in the problem? As long as those two things match, I know I have the proper answer. So we can finally check our answers in this calculus course.